We're going to start the last section of kinetics, and that is on reaction mechanisms. This is a somewhat abstract idea. I think it's hard for people to envision the molecules because they're so small. So this is traditionally something that's very confusing for students, and so hopefully that won't be true for you. If it is, then certainly come and talk to me about it. So reaction mechanisms, what that means is that many reactions, it's sort of the steps in a reaction, and it describes the physical molecules that collide with each other in reality in each step of a reaction. So the example from your book is a two-step reaction where in step 1 we have a molecule of nitrogen dioxide colliding with another identical molecule of nitrogen dioxide, and those form one molecule of nitric oxide and one molecule of nitrogen trioxide. And then in step 2, that nitrogen trioxide will then react with a molecule of carbon monoxide, and that will reform one of the molecules of nitrogen dioxide and a new molecule of carbon dioxide. And so you're supposed to see, let's see, the little faded colors that you see around the atoms are supposed to give you the feeling, the indication that the reactants on the left in both steps 1 and 2 are colliding. They're running into each other, right? They're moving toward each other, and that the molecules on the right in both steps, the products, are separating from each other. So they're moving away from each other. And so the idea here, the reason they add those little faded lines is to make sure that you guys understand that these are the actual steps that are going on in the reaction, right? These molecules are literally colliding with each other in 2 steps. Now, the issue with reaction mechanisms is that we normally don't know what the mechanism is because we can't see these intermediates. They're just too short-lived. And so traditionally what we see is the overall reaction. So that's the first thing I want to talk about. We think about this, the overall reaction, what we see going into the reaction, whatever we put in the beaker, and what we see coming out of the reaction, whatever's there in the beaker at the end. That's really all we see. So we think about that as the overall reaction. And so if you look at the particular example we have here, if you notice there are 2 molecules of NO2 going in step 1, but one of them is reformed at the end of step 2. And so really the overall reaction, you only see one of those NO2s going in. So we're going to make this one disappear and we're going to make this disappear because the overall reaction, there's just a single NO2 reactant. Since you consume one but then reform it, it's like it never happened magically. So another molecule on here that you wouldn't see in the overall reaction is NO3, which is one of the products of step 1, right? So on the right you see nitrogen trioxide being formed, but it is immediately consumed in the very next step. And so you wouldn't actually see that ever in the beaker. It doesn't go in and it doesn't come out. And so we're going to make him disappear and the reactant in step 2. So now if you look, this is the overall reaction. What you would see going into the beaker is NO2 and carbon monoxide, CO, and what you would see coming out of the reaction is NO, nitrogen monoxide, and carbon dioxide. So when we talk about reaction mechanisms, we don't usually use models. We usually just draw it in a reaction, in an equation. So let's talk about the first item here. Reactions that occur in one step are called elementary reactions. So some reactions are only one step, but and for an elementary reaction, the rate law would be determined strictly from the stoichiometry of the reaction because it is a single step reaction. For example, here we have a molecule of A colliding with a molecule of B to form C and D. And so in this case, the rate law would be first order in A and first order in B, because we know that one molecule of A must collide with one molecule of B. Now, many reactions are multi-step, and that is why, unless you know it is an elementary reaction, you have to determine the rate law experimentally, because you don't know if it occurs in one step or in multiple steps. So if we look at a multi-step mechanism, which is the typical case, this is a written out in equation form for the same example we just went over. So we have 2 molecules of NO2 reacting to form one molecule of NO3 and one molecule of NO. So one of those oxygens just simply got transferred to the other molecule of NO2. And then there, next to that, it says slow. That means that time-wise, this is a slow step. And then the subsequent step here is NO3 collides with carbon monoxide to reform a molecule of NO2 and CO2. So in this case, you can think about NO3 as sort of a middleman in this. He takes the oxygen and then he transfers it to carbon monoxide. And so he's sort of a middle of the road guy, right? He's the middleman in the transaction. So the second step there is listed as fast, and that would be relative to the first step, which is slow. So again, if we look at the overall reaction, then we put a line here, we cross off anything that's on the left and the right, and that leaves us with NO2 plus CO react to form NO and CO2. NO3 is defined as an intermediate in this reaction. So an intermediate is a molecule that is created in an early step but is consumed in a later step. So you don't actually see it in the overall reaction. The slowest step is defined as the rate determining step, and the reason it's called that is because it alone determines the rate of the reaction. The rate determining step in the mechanism that's shown here is step 1, because that is simply the slow step. So rate determining steps are described that way. It's always the slow step, and the best example I can think of is when you're paying a toll. Back before you could pay electronically with E-ZPass, you used to have to give change to the plaza, the woman at the toll plaza, and if there's a really slow person, if you look at the picture on the left, A, Plaza A must be really slow, and Plaza B is a really fast change producer. And so in that case, all of the cars back up at Plaza A. And then as soon as they pass through, because Plaza B is so quick, they just stream right through. And so the overall rate of getting through A and B is really determined only by the slow step, Plaza A. And then in the second case, the case on the right, you can see that Plaza B is the slow step. And so again, Plaza A, they would travel through very quickly and they would get backed up. The bottleneck would be Plaza B. So the overall rate would be determined by the rate of Plaza B. And so Plaza A is so fast that it doesn't influence the overall rate. So the rate determining step is always the slowest step. And the rate law, the overall rate law that we've been talking about, first order, second order, that can be written from what's called the molecularity, which is just the stoichiometry of the rate determining step. So we use the word molecularity to describe the number of molecules that collide in a given step, in a given what's called an elementary step, which would be the individual steps of the mechanism. So you can see here in table 12.5 that if A reacts to form products, this is called a unimolecular reaction, the molecularity would be 1. Then the rate law would be written as rate equals K times A, and it would be A to the first power. So elementary reactions on the left, remember, are single-step reactions. Or if this is simply a step in a mechanism and you know it is the rate determining step, then you would call that an elementary step. And if it is the rate determining step, you can write the rate law straight from the molecularity. So the second example, A plus A collide to form products, that is a bimolecular reaction, or the molecularity of 2, because 2 molecules must collide in the rate determining step. And then the rate would be, the reaction would be second order in A, because there are 2 molecules of A that have to collide. So you can look at all of these examples and you can see that if it's an elementary reaction or a single step reaction, or if it is the rate determining step in the mechanism, you write the rate law straight from the stoichiometry of that rate determining step. Now we're going to practice this problem. We're going to go one step at a time to make sure everybody understands mechanism. All right, so we're going to start with this first problem, and we're going to put the other problems after this one. I think there are 5 total problems on mechanisms. All right, so we have a mechanism here. We're going to start with part A with writing the balanced equation for the overall reaction. So you just take the mechanism in each step, and you need to just draw a line and write the overall reaction. You're going to cross off anything that's on the left and on the right. Hypochlorite, chlorine monoxide, is an intermediate. which we'll talk about. And then chlorine, atom of chlorine there appears to be a catalyst, which we will also talk about. And so when we cross off what's on the left and on the right, that leaves us with 1O3, ozone, plus 1 oxygen atom leads to 2 molecules of oxygen, molecular oxygen. That's our overall reaction. So we'll circle that. Let me know if that doesn't make sense. Move on to part B. Identify all reaction intermediates. So the reaction, and then we'll look at catalysts at the same time. So let's talk about what these two mean. Okay, an intermediate is a molecule that is formed in an early step and then is consumed in a subsequent step. Because it's formed and then consumed, you only really see what goes in and what comes out, and it appears that the intermediate was never there. We don't write it in the overall reaction equation. So in this example, ClO, chlorine monoxide, is the intermediate. Catalysts are molecules or substances that are consumed in an early step. Their presence must enhance the rate of the reaction, which is why they are catalysts. And then they are reformed in a later step. They also do not appear in the overall reaction because they're both on the left and the right-hand sides of the equation. So in this particular example, the intermediates, again, that's chlorine monoxide, ClO. We'll underline that in red. And then the chlorine atom here is our example of a catalyst. We'll underline that in orange. So there's my answer. The intermediate is ClO gas. C, the catalyst is chlorine gas. Now we'll move on to the next question. What is the molecularity of the rate determining step? Now we need to start with what the rate determining step means. That is always the slowest step in the mechanism. That is, by definition, the slowest step is the one that determines the overall rate. That means we could write the rate law strictly from the molecularity of that step, the stoichiometry of the rate determining step. So our rate determining step is step number 1, which is the slow step. And the molecularity in that case is 2. It has 2 molecules that collide. Because there are 2 molecules that collide, it is a bimolecular reaction. Since 1 chlorine collides with 1 ozone, that's 2 molecules total. 1 and 1 makes 2. You might also call it a bimolecular reaction or bimolecular step. That was part D. If we move on, part E, the experimentally determined rate law is given here. That would be one that you would go in the lab and figure out. It is first order in chlorine atom and first order in ozone. And the question is, does that rate law corroborate or refute the proposed mechanism that was provided? And you explain how you know. So the rate law is related to the rate determining step, so that matters, right? You look at the rate determining step and you write the rate law for that. The expected rate law for this particular mechanism would be rate equals K. You always need the rate constant. And it's chlorine to the first power because there's 1 chlorine atom in the rate determining step that collides with 1 ozone molecule in the rate determining step. So based on this provided mechanism, you would expect this reaction to be first order in chlorine atom and first order in ozone, which it is. So you would say, yes, it corroborates. So here I've drawn some 1s up here, and that goes with the stoichiometric 1s in the rate determining step. So you would say, yes, therefore the experimental rate law corroborates this mechanism. Because the rate law I would write from the stoichiometry of the rate determining step matches the experimentally determined rate law. So we're going to move on and do mechanism problem number 2. Here we have boxes that represent different starting amounts of 3 different reactants. A is red, B is blue, and C is yellow. And then we also have relative rates provided, 1 to 2 to 1 to 2, which means that if 1's rate is considered some value, 1x, then by comparison, the second box results in a doubling of that rate, or 2x. Box 3 would have the same rate as box 1, so it's 1x. And box 4 would have double the rate of box 1, so it's 2x. And it would have the same rate as box 2. They're both 2x. So let's start with part A. I'm going to write the differential rate law, which means we need to look at how the reactant concentrations change and the effect that has on the rate. So here, if we look at box 2 and we compare that to box 1, in box 2, it appears that we have 1, 2, 3, 4, 5, 6 A atoms, but we only had 3 in box 1, so we've doubled the concentration of A. And the corresponding effect on the rate is that the rate has doubled. So if the rate doubled and the concentration of A doubles, that means that this is first order in A. And if we move on and we look at 3, box 3, we're going to compare that to the original box, box 1. And here we're going to look at B molecules. So we have 1, 2, 3, 4, 5, 6 B molecules, but we had 3. So we've doubled the B concentration from reaction 1, but that did not affect the rate. The rate stayed the same. So when the concentration of B was doubled, the rate was not affected, which means that it is 0 order in B. Okay, so first order in A, 0 order in B. And then if we look at box 4, we're comparing C. It's the one remaining reactant. So we have 2 C's, and in box 1 we only have 1, so we've doubled C. And if we look at the corresponding effect on the rate doubled. So that means that this is first order in C, because whatever we did to the concentration also happened to the rate. So if we write the rate law, we're going to write the normal form of the rate law, which is rate equals lowercase k times concentration of A to the first power times concentration of C to the first power. We're going to move on to part B. We're going to write a plausible mechanism that's supported by the observed rate law. And I'm going to write the rate law that we determined in part A. So a plausible mechanism, there are a lot of different possible answers for some of these questions. It just means that the rate determining step needs to have the stoichiometry. You must have 1A colliding with 1C, and that's the only real requirement that that be in the rate determining step. Usually we make that the first step, the slow step. So A plus C collides to form some AC intermediate. The other important piece of this is that the overall reaction, A plus B goes to AB, that must be the overall reaction we get when we combine the individual steps. So that means AC must go away. It must be an intermediate that collides with B to form AB. And C must also go away because it's not in the overall reaction. So C appears to be a catalyst, AC appears to be an intermediate. When we add these together, C goes away and AC goes away, and we get A plus B goes to AB. So that is the overall reaction we're looking for. Again, there are possible multiple steps, multiple answers to this. Now if we look at the mechanism we gave and we identify catalysts and intermediates, remember that catalysts are initially consumed and then reappear usually, so that would be C. Intermediates are something that are formed in an early step and then they are consumed in a subsequent step, so that would be AC in this example. We're going to go on to a third mechanism problem. So we have boxes again representing initial conditions. For 2A plus C2 goes to 2AC. I've labeled A, which is the red spheres, B is the blue spheres, and C are the yellow spheres. So I've labeled everything on there. And the relative rates of each box is 1 to 1 to 2 to 3. So that means that box 2 is the same rate as box 1, box 3 is twice the rate of box 1, and box 4 is 3 times the rate of box 1. So first we're going to write the differential rate law. In order to do that, we need to identify how the reactant concentrations influence the rate that is observed. So we're going to compare boxes 1 and 2, and it appears that we have doubled the concentration of A. So 1 is our comparison reaction. It has a relative rate of 1. And then if we're determining the differential rate law, we need to identify what x, y, and z are, right? So those are the powers in the rate law equation. So if we look at 2, we're going to start by identifying what's happened. So we've doubled the concentration of A, but the rate is the same. It has not changed. And we know that because the relative rate is 1. So the rate remains unchanged, which means that this is 0 order in A. A has no effect on the rate. So we know x is a 0. Now if we look at box 3, what's happened is we've doubled the concentration of C2. And we're comparing it to box 1 again. That's going to be our comparison for the entire problem. We doubled the concentration of C2, and the relative rate is 2, which means the rate doubled. So what that means is that this reaction, since the same thing occurred to the rate that we did to the reactant concentration, it must be first order in C2. So that means y is a 1. Now, reaction 4, I'm guessing it's going to be B. So if we look, we've got 2 B's in box 1, and we've got 6 B's in box 4. So the concentration of B was tripled, and the rate is tripled. So what that means is that this is first order, because the rate triples. The same thing happens to the rate that what happened to the concentration of B, which means that the exponent z is a 1. So the rate law is rate equals k times C2 times B, both to the first power. If we move on to part B, we're going to write a mechanism that is supported by the rate law. So the important part about mechanisms, and you might have a large variety of answers for part B. The important part is that the rate determining step in your mechanism, the slowest step in your mechanism, needs to reinforce this rate law that you determined in part A, which means that you need to have 1 molecule of C2 colliding with 1 atom of B in the rate determining step. The stoichiometry has to be a 1 and a 1, and nothing else can be in the rate determining step. So the mechanism depends on the rate law, and the overall reaction has to be the sum of all the individual reactions. So we have to keep both of those things in mind, the rate law and the overall reaction. So if you look at the observed rate law, it's first order in C2 and first order in B, which means that those 2 molecules must collide in the rate determining step of my mechanism. And the overall reaction is important because the individual steps in my mechanism must add up to the overall reaction. So I'm going to write this mechanism. It's easiest to start with a slow rate determining step and just include the 2 items in your rate law in that step. So I have an atom of B colliding with a molecule of C2, and the products that form, you can kind of envision maybe they all split apart, maybe B combines with C, but there has to be something on the right that's different than what's on the left. And this is one way to do it. Step 2, you have to have, keeping in mind the overall reaction, that means that anything that was formed in my first reaction, my first step, anything that was formed there that's not in my overall equation must be consumed in a later step. So that means that this BC here, this is an intermediate, and I know that because it doesn't appear in this reaction equation. So I have to use that up in step 2 or step 3. But if we take our first intermediate BC and we combine that with an atom of A, and the reason I have to add A in is because I've got 2 A's up here. I have to add those in at some point because they're in the overall reaction. And in this step, it looks like BC, this molecule is donating its C over to the A. So a new bond is forming between A and C, and then that releases the atom B. So we'll make that a fast step. My intermediate is consumed. But now if you look at this, I need a third step, because if I add steps 1 and 2 together, I don't get the overall reaction yet. And the reason for that is because this other intermediate that I formed, C, doesn't appear in the overall reaction. So I'm going to have that combine with an A in a third step. so that now when I add all these together, I should get the overall reaction. That third step should also be fast. I didn't include that there, but it should also say fast next to it. I'm just verifying here that they add up to the overall equation, which they do. There, I added the fast there. That should be on there. And remember that the two molecules that are in the rate law appear in the rate determining step. That's important. Slow step. Part C, identify any catalysts and intermediates. If we come back to our mechanism that we made, remember that a catalyst is in any substance that is consumed in an early step but then is reformed by the end of the reaction. That would be B. B is reformed in step 2. It does not appear in the overall reaction equation. And then the intermediates I'm going to do in green. And the intermediates here, we have a couple of them. BC is created and then consumed in step 2. And then the intermediate C is created in step 1 and then consumed in step 3. So those would both be considered intermediates. They also do not appear in the overall reaction equation. That says 2 intermediates. Here's a fourth problem. The following diagram represents an imaginary two-step reaction. Let the red spheres be A, the green ones are B, the blue ones are C. Write the equation for the net reaction that is occurring, identify the intermediate, identify the catalyst. This one's a little bit different than some of the ones we've been looking at. These boxes represent the steps, okay? So there's a first step that goes from box 1 to box 2, and then a second step goes from box 2 to box 3. So these boxes represent the reaction. If you could put on your molecule glasses and look at the reaction as it's occurring, these would be the 2 steps in the reaction. The 2 arrows are the 2 steps. So this is not what we've been used to looking at, which are different initial conditions in each box. This is actually a series of steps in a given reaction. So this is a mechanism. They're just doing it in cartoon form. So I'm going to label the atoms again so that we know what they are, and I've labeled the steps here, step 1 and step 2. So I've labeled all the atoms, and we've got the 2 steps. Step 1, we have A2, that's shown here, and that's combining with AB, and they're going to form 2 molecules of ABA. Now, CA I'm ignoring here because it appears in both box 1 and 2, so that must be a second step of this equation. So my products for step 1 are A2B and 2A. I need a 2 here in front of this. I forgot to add that, but I'll add that later. The second step, we have AC, which remember has just been hanging around, not doing anything. See how he's hanging around in box 1, but he looks the same in box 2, so nothing happened to him there. So he's just been sitting waiting for step 2 to take place. Step 2 is going to involve the conversion of Ca. It appears that Ca is going to transfer its A atom to this A atom, and then it's going to be C all by itself here, and then 2 A2s. So AC combines with an A atom. There I added the 2's. I forgot to put those on there. I still forgot to put the 2 in front of this A2B. I need to add that. And then we have 2 A2's forming. Those are here. And then we have 2 C atoms left over. So the net reaction, if we combine these 2, you cross off things that are on the left and on the right, so 2 A's, and we have 2 A2's, so we have 2 AB plus 2 AC. There still needs to be a 2 A2B there, I think, right? Yeah, we end up with 2 A2B's at the end. There should be a 2 in front of this, a 2 coefficient right here. Can't remember if I remember to add that later or not. Part B, identify the intermediate. Intermediates are formed in an early step and consumed in a subsequent step. They do not appear in the overall reaction. So if we go back to our mechanism, 2A is an intermediate that's consumed in step 2. So that's my intermediate. And then we're going to identify the catalyst. Catalysts are used up in an early step and then reformed in a later step. They also do not appear in the overall reaction. So if we go back to our mechanism, the catalyst in this case is present at the beginning and then it's reformed later. So 2A2 is our catalyst, or A2 is the catalyst. You can put the 2 in front of it if you want, but you don't have to. Another way to do part A, by the way, if we erase this, I'll leave the answer to part A from the original equation. You can just look at what's present in box 1 and box 2 and box 3, right? Box 1 is what goes into the reaction. Box 3 is what comes out of the reaction. If you cross off anything that's present in both boxes, what goes in, what comes out, what goes in is just the reactants, what comes out is the products. So you have to ignore things that appear the same in both boxes. They're just floating around. It looks like they're not doing anything. That's the catalyst. All right, so the catalyst, A2, appears to be doing nothing. It doesn't appear in the overall reaction. Even though it is doing something, you can't see it. So it looks like it's just floating around. So the overall reaction matches here, right, where you just add up, you see what's present at the start. There's 2 ABs and there's 2 ACs, right? I think here is where I realize I'm missing my coefficient, and then what comes out goes here, right? So we have A2B. This is where I add my 2 because I forgot it earlier. The fifth and final mechanism problem is here. The following reaction is an elementary reaction with a rate constant given here. Calculate the concentration of A at 125 seconds if the initial concentration of A was 0.25 molar. Now this looks a lot like an integrated rate law problem, which it is. What makes it a mechanism problem is the fact that it calls it an elementary reaction. So that gives you a clue about the rate, okay, it's the rate law. So if this is an elementary reaction, that means it occurs in one step, which therefore means you can write the rate law from the stoichiometry, which is the same as the molecularity, in an elementary or single step reaction. Because this says a 2 in front of the A, what that means is that a molecule of A collides with another molecule of A in a single step to form 1B. And so therefore the reaction, the rate would be second order in A. So we need the second order integrated rate law. And so we're going to write that down and then solve the problem. So the second order rate law from your yellow sheet, that's right down here, right? There's the second order rate law. We write that down and we fill in the numbers. So calculate the concentration of A. That means we're going to solve for this A at time t. 125 seconds is t. Initial concentration of A, 0.25 molar, goes here. And then the rate constant is given in the problem up here at the top. So we plug those numbers in. And you get this. And if you plug that into your calculator, you get this. You hit the 1/x button on your calculator and that will invert it. And that means the concentration is 5.5819 times 10 to the minus 4. The concentration is going to be molarity because my rate constant is in per molar per second. And my initial concentration is in molar. And so sig fig wise, we have 3 sig figs. We have 3 sig figs here, which means that this 1785 number is only accurate to 3 sig figs. And then this 0.25, when we invert that, you get 4.0, and that has 2 sig figs. When you add 1787.5 to 4.0, this is accurate to the tens place. This is accurate to the tenths place, which means the 1791 number is only accurate to this 9. right? That's the tens place. And that means this number, 1791, that has 3 sig figs, which means my final answer should have 3 sig figs, which is going to be 5.58 times 10 to the minus 4 molar. So I erased a little bit to make it my final answer, and there's my final answer.